Hello and welcome to this video lecture on the linearization method, which is also known as Lyapunov's indirect method. This method allows us to study the stability properties of certain non-linear dynamical systems. The main idea is that we linearize our non-linear dynamical system. We approximate it, that is to say, by a linear system. We then solve Lyapunov's equation to determine a Lyapunov function for the linear system. And we want to see whether this Lyapunov function, whether this quadratic Lyapunov function satisfies an LDC for the original nonlinear system over a certain invariant set. And the answer actually is affirmative under certain conditions. So let's start by having a look at the dynamical system. So consider this dynamical system, xt plus 1 is equal to f of xt. Of course, xt is a vector like this, x1, x2, x3, up to xn. Xt plus 1 is another vector, so this function f maps vectors to vectors. It's a function like this. It returns a vector with elements f1 of x, f2 of x, down to fn of x. It's a function from Rn to Rn. We will introduce an additional assumption here. We will assume that f is smooth in a way. We will say that f must be continuously differentiable. This is something we hadn't assumed previously when we studied the three stability theorems of Lyapunov. And as before, we will assume that f at 0 is equal to 0, apologies, or that 0 is an equilibrium point of the system. The origin is an equilibrium point. When we say continuously differentiable, we actually mean that the function has a derivative. It's not called a derivative. In fact, it's called a Jacobian matrix. More about this in one moment. And that this is a continuous function. For this function f, and under this assumption, by Taylor's approximation theorem, we know that function f can be approximated around the origin by a formula as simple as f of x is equal to matrix times x plus error, where this matrix A is the Jacobian of f at 0. Imagine like derivative times x plus error. Or you can simply write f of x is approximately equal to A times x. Or f of x equals to ax plus, let's not write error, you can even write a function h of x. But that's the thing, you can approximate your f by a linear function. That's the idea. Now, what is this Jacobian of f? This Jacobian of f, think of it as a generalized derivative for functions that map vector to vectors. It's a matrix. It's a matrix like this that contains partial derivatives. It contains the partial derivatives of f1, f2, f3 up to xn with respect to x1, x2 down to xn. So it's all the partial derivatives of f put in a matrix in this order. So the rows are f1, f2, fn. The columns are x1, x2 up to xn. This is the Jacobian of f. We assume that f is continuously differentiable. We need one more assumption. To move on from here. We need to assume that the Jacobian is Lipschitz. Is Lipschitz with constant L. What we're trying to do here is we're trying to see how good the linearization is. How approximate is it? How big is the linearization error? And for that, we need to introduce the following assumption that the Jacobian of f is Lipschitz with constant L, or we simply write L Lipschitz. What does this mean? It means that there is a constant L, there is a constant number L, such that this inequality holds for all points x and x star. Let's read it out. The Jacobian of f at a point x minus the Jacobian of f at a point x prime has a norm that is controlled from above. It is less than or equal a number L times the norm of x minus x prime. This is often the case, not always, but it's often the case. And it simply says that the distance between Jacobians at x and x prime is controlled from above by the distance between x and x prime. As x goes closer and closer to x prime, as x and x prime approach one another, and the distance between them becomes small, so as the norm between x and x prime becomes small, the distance between the Jacobian of f at x and the Jacobian of f at x prime also becomes small. There is a little catch here. X and x prime are vectors. So this is a vector norm. These are matrices, and here we have a matrix norm. But that's all really. Now, if this is the case, under this assumption, which holds only sometimes, not always, the linearization error, so the difference between f of x and a times x, so what we previously denoted as h of x, the error h of x, is less than or equal L half times norm of x squared. So at the end of the day, we have the dynamical system. Let me write it down once again. xt plus 1 is f of xt. This is the original dynamical system, which we can write absolutely equivalently like this. xt plus 1 is, I'm writing f like ax plus error. Linearization plus the remaining part, h of xt. A is the Jacobian of f at 0. And I know one thing about the linearization error. I know that the linearization error is less than or equal a number times the squared norm of x, which means practically that as x becomes small when I'm close to the origin, so the norm of x is small, this implies that the linearization error h will be small. It will have a small norm. So this inequality you see here controls the linearization error. And this is precisely why I had to assume this Lipschitz condition. I have written here that this is an exercise. I have given a hint in the handout, and you can try this for yourselves. But for now, in this presentation, let's take it as a fact that the Lipschitz condition implies that the linearization error h has a norm that is less than or equal this quantity, L half times the norm of x squared. And let's take this as a fact. Why do we need this? We need this, and I'm saying this because I'm really encouraging you to try to prove this theorem as an exercise. We need this to prove this wonderful result. And let's read it out. It says that suppose that this function f is continuously differentiable and the Jacobian is Lipschitz with a constant L. I should have written L Lipschitz, although L doesn't really show up in this theorem. So Lipschitz with some constant L, we don't need it here. And let us denote by A the Jacobian of f at 0. Then look, if the spectral radius of A is less than 1, so if the linearization as a dynamical system, if the linearized system is stable, then the origin is locally exponentially stable for my original dynamical system. On the other hand, if the spectral radius of A is above 1, the system is unstable. So I would strongly encourage you actually to prove the first part. And you can prove the first part by following the procedure I have outlined below. You start with a non-linear dynamical system. You linearize it, as we did before, and you end up with xt plus 1 is axt. A is this matrix. Then you solve Lyapunov's equation. Actually, you don't need to solve it really, just say I'm choosing my matrix P to be the solution of this equation for some matrix Q. It doesn't matter. You can even take Q to be the identity matrix if you feel comfortable with it. So just say I'm choosing P to be a solution of this equation. You don't need to solve it because you know the solution exists. You can go to Python and you can determine it. Now take this P from here and define this Lyapunov function. This Lyapunov function is actually a Lyapunov function that satisfies LDC for the linear system, not necessarily for the non-linear system. Here's the thing now, that's the interesting part. We need to show that this Lyapunov function satisfies an LDC for the non-linear system. What are we trying to prove? We're trying to prove that the energy at the next state of the non-linear system minus the energy of the state at the current, minus the energy of the system at the current state is less than or equal minus x transpose qx for some matrix Q. So if you substitute f of x equals ax plus h transpose times p times ax plus h of x minus v of x, which is, by the way, I should have written here simply to make things simpler, x transpose px is less than or equal minus x transpose qx, all right? But we know a few things about h. What do we know about h? Here we will get some help from the assumption we drew at the beginning. So we know that the norm of h is less than or equal L half times norm of x squared. So you need to use this as a useful tool in your proof to show that such an inequality is satisfied. That such an inequality is satisfied over an invariant set. Now that's the difficult part of the proof, but I'll give you a hint. Previously, in the previous video lecture, we said that if we have a function that satisfies an LDC, then there is a way to determine an invariant set. So this should give you a hint. Try this as an exercise. I think it will be a very useful exercise to actually understand and appreciate how Lyapunov's theorems can be used in practice. But let's have a look at the theorem once again, because it also makes sense to be able to understand and use this theorem in practice. I'll read it once again. Suppose that my function is continuously differentiable and has a Lipschitz Jacobian, and I'm taking A to be the Jacobian at 0. Then focus on this matrix only now. If the spectral radius of the matrix is less than 1, the origin is locally exponentially stable for the non-linear system. If it is above 1, the system is unstable. If it is equal to 1, this theorem doesn't tell us whether the system is stable or unstable. So we shouldn't really rush into conclusions. There are other theorems that can help us take it from there if we run into such a situation. But if it is equal to 1, there is nothing we can say. If it is less than 1, the system is locally exponentially stable, otherwise it is unstable. That's all we know. Also pay attention here, it says locally, not globally. Locally exponentially stable, exponentially, apologies for the typo. Example. Okay, so take this dynamical system. We have a state x that comprises A and B. A at time t, B at time t. It is given by this nonlinear function over here. Now take the Jacobian. This is my Jacobian. And take the Jacobian and determine it at 0. Here it is. The eigenvalues of A are 1/3 and 1/2. There is just something little missing from here. We haven't shown really that the Jacobian of F is Lipschitz. We haven't done this part, but we're not doing this now. Okay, if you like, you can try this as an exercise, but I will not prove to you that this is Lipschitz. In fact, it is sufficient if you try to prove that it is Lipschitz. Don't try to prove that it is Lipschitz throughout the whole Rn, but try to show that this is Lipschitz locally. This is absolutely sufficient. So you will be able to do that if you try. If not, we can discuss next time in class. Take this matrix A, which is the Jacobian of f at 0. You determine this matrix, you see it is 1/3, 1/2, it's diagonal. So what are the eigenvalues? 1/3 and 1/2. Which one is the largest one? It is 1/2. It is less than 1. It is less than 1. Therefore, the origin is locally exponentially stable for the nonlinear system. I didn't dwell too much on how to determine the Jacobian of this function, but I believe it's quite straightforward. So you have this function f. Let me show you, for example, this one over here. So this element is the partial derivative of f2 with respect to x1, which is the derivative with respect to x1 of what? Of 1/2 e to the a b. Actually, I wrote x1. I should have written a. A is my x1 here. A is my x1. So it is 1/2 b, and then e to the a has derivative e to the a. And that's why I have here 1/2 e to the a b. So it is really straightforward to determine the Jacobian. Take the Jacobian, evaluate it at 0, put a equals 0, b equals 0. You will find this matrix here, 1/3, 1/2. What's the spectral radius? 1/2 less than 1. That's it. My system is locally, the origin for my system is locally exponentially stable. For the same system, this is what we can do now in Python. If you don't want to do this whole thing on paper, or if you have a very complicated system, you can use the symbolic library of Python, SymPy. You can use SymPy. Define x to be the vector ab. So here I have actually written x equals ab, just that. F is, I have just copied from here. This is my f. I have copied this function into Python. A times 1/3 plus cosine of b minus 1. And the second element is 1/2 exponential of a times b. The Jacobian of f is computed by Python. I don't have to do it myself. If you're lazy, you can do it in Python. Then jf0, this quantity, is my matrix A. This is the Jacobian of f at 0. You can print it to see how it looks like. And you can then also, if you like, you can determine the eigenvalues in Python as well. So if you have a very big function that is complicated and it would take you a while to do the derivation on paper, you can use a symbolic library or software to determine the Jacobian if it is lengthy or complicated. This is how a trajectory of the system looks like. In this graph, the horizontal axis is x1, the vertical axis is x2. I'm starting from minus 1, 1. And you see how the system goes towards the origin. The origin is here. And you can see the energy of the system. Here I'm using V of x is x transpose px, where P is the matrix I have determined by solving Lyapunov's equation. A transpose PA minus P is equal to minus Q. In this case, I have taken just the identity matrix. So I have determined such a matrix P. And you see how fast, exponentially fast actually, my energy dissipates. Once again, you can try to prove this result yourselves. And this is an exercise of espresso index 2. So you will need 2 cups of coffee to solve this. It's generally not very straightforward, but once I give you this hint, it becomes straightforward. So apply this hint. The hint says, use the fact that from the fundamental theorem of calculus, we can express f in terms of its Jacobian. So what you have to do is just substitute f equals and replace by this integral, and then the result will be a lot easier. Start from here actually, put f from this formula and gradually try to show that this is less than or equal, less than or equal, and so on, and try to show that this is less than or equal L half times norm of x squared. But do use the hint and the problem will become easy to solve. So really take f and put it here. Another exercise is the linearization theorem itself. This is a problem with espresso index 4, so it is a little challenging, but it's not so difficult if you follow this recipe we have here. Again, take the nonlinear system, linearize, solve Lyapunov's equation, define this function, and this is what you're trying to prove now. This is exactly what you're trying to prove, and use the previous result. In fact, this was part of a coursework assignment a couple of years ago. And yes, here's another hint as well. And then you can do something a little more applied, just apply the theorem directly. So I have a couple of exercises here, number 8 and number 9. You can find these in the handout, actually. So take a dynamical system like this. You'll have to follow the standard procedure. Take f, find the Jacobian of f, substitute x equals 0, so determine the matrix A, which is the Jacobian of f at 0, then find the eigenvalues of A and determine the spectral radius of A, and then there are three possibilities. One is that this is less than 1, so the system is locally exponentially stable. The other possibility is that it is above 1 and the system is the origin is unstable for the system. And there is the borderline case, which is equal to 1, which is unfortunately inconclusive. We cannot draw any conclusions if it is equal to 1. So in that case, maybe it is locally exponentially stable, or maybe it is attractive, maybe it is not even attractive, maybe it is Lyapunov stable, maybe not. We don't know. The theorem cannot give us any more insights, this theorem at least. And there is another exercise of exactly the same type. So thank you very much for watching, and goodbye.